我是从来不认为哪样课值得修第二次。差不多开始吧。James， 你这边准备好了吗？
哎，好了。
Okay, so welcome back. So last class we mentioned about gradient. So basically the gradient operation operates on a scalar function. Right, so you have a scalar function. It is a perimeter of space, two-dimensional, three-dimensional, but it is scalar, meaning there's no direction, there's only value. Before its gradient, you're trying to find the maximum amount of change in certain direction. So we use a map of height to serve as an example. So after you perform the gradient operation, you have a vector. So today, we are going to introduce another operation, which is called divergence. Okay. So mathematically, divergence is written as the same inverted triangle, but now having a dot function. To remind you, this operation is working on a vector. So I'm using the color yellow to denote a vector, and the green one to denote a scalar function. So divergence and gradient are somehow reversed. Divergence works on a vector function, but then you arrive at a scalar function, right? So this is in contradiction to gradient. Gradient operates on a scalar function, and you result in a vector function. Okay, reverse. So we can turn off the light. So now let's come back to the PowerPoint. Before we begin, let me show you a nice picture. So if you see the title of this slide, it's Divergence for Fun, right? So math can be fun. I know it's very difficult for you to find, but I'm trying my best. So let me show you a very beautiful picture. So this is something you go into a water park, and you might see this. So magically, there is a water outlet, right? There's no water coming in because there's no wall. But magically, you have water flowing out. So think about it. Try to relate this magical water outlet to divergence, and then try to understand what does it mean when you perform a divergence on a vectorial function. So there's no water coming in, but there is indeed water coming out. So if I ask you to calculate something, right? For example, I have a box. I have a three-dimensional box to surround this entire outlet, and I ask you, what is the net flow of water coming out from this yellow box? From this side, no water coming in. This side, no water coming in, no water coming, only water coming out, right? No water coming in, no water coming in here and the back side. So there are 5 sides without water coming in or out, but there's only one side having water coming out. So you will answer me, this is really magical. This really contradicts to our understanding. Usually you have the wall, the outlet. You know water is coming in from this side and water is coming out. So there's no net flow of water. But in this case, if this is true, of course you know how it works. There's a center tube having water coming in, and it's just coming out from the outer tube. So the total mass, the amount of water, is still conserved. But I'm using this example. If you don't know the trick, how it did it, in the space, you just have water coming out. And that really relates to what divergence means physically. The meaning of divergence is you're trying to sample the net outward flow or flux of your vectorial field in a small volume, a three-dimensional volume. Okay? So this is what you have to remember forever. As you can see, the way I'm teaching vector analysis or calculus, I'm not emphasizing on the derivations, but rather on the physical meanings. If you can understand and embrace the physical meanings, you don't really have to memorize a lot of this, right? So for divergence, the definition is you're trying to sample. So you have a vectorial field. A vectorial field, A, may be drawn as these lines. Okay, so it's like some kind of flow of water. So for me, the best analogy to think of the fields is like water, because we encounter water every day. Water is like something flowing with certain velocity and direction. So it's a very nice analogy example to serve for our understandings. So you have some flow of fields or flow of water, and you just place a cube, right, into it. And you ask yourselves, what is the net flow of water in that cube? So in this case, water is coming in from the left-hand side, the surface, and the same amount of water is flowing out on the right surface. So the net flow of that vectorial field is 0. Now, if you have the definition and you come back to this example again, you have your space, right? You use this yellow box, a three-dimensional box, to surround this outlet. And then you ask yourselves, what is the net outward flow of field? Field here is represented by water. Ideally, I mean, if you don't know the trick, you have water flowing out. So the net outward flow is positive because water flowing out is outward. Okay, so it is positive. So if you have a divergence of a vectorial field, meaning the net outward flow or flux is positive, then this is telling you in the space you surrounded, there is a source of the field. Okay, so this is a flow source. So let's come back to this picture. So somewhere you know this yellow box is giving you water. So if you ever become thirsty, you just go there, right? It's magic. You just go there, you don't have to provide water, but you have water you can drink. Of course, it's magical, it's just a trick. But on the other hand, if the divergence of that vectorial field is negative, what does that mean? You perform divergence of a vectorial field, but then you have a negative value. Scalar can be positive or negative. It doesn't matter. But if you have a negative value, it means water or field is flowing into it, right? So basically, I didn't mention about the flowing direction, but ideally we think due to gravity, water is flowing downwards, right? So this is flowing out, but it can also flow into the outlet, right? So in that case, if you have a negative divergence, water is flowing from the bottom to the up. This is more magical, right? So I pretty much gave you the definition. Again, try to repeat after me. Divergence works on a vectorial field, and when you perform the divergence, you're trying to calculate or trying to ask what is the net outward going out. If you have a positive value, you have fields going out. Okay? The net outward flux per unit value. So this is something you have to remember. The meaning is you have a three-dimensional solid structure and you are trying to sample how much of the field is flowing out. And net means you might have certain surface flowing in, so it takes on a negative value, but then maybe another surface is flowing out, it takes on a positive value. So positive and plus negative, does it go to zero? So this is extremely important for you to understand, right? So mathematically, I know you hate math, so do I, but let's try to write this sentence using a mathematical equation. For me, if you can write something to represent some wording, you feel you are superior, you're better, you're good. Okay? So divergence, defined as the del operation having a dot on a vectorial field, is defined as for a very small value, right? Unit value. So in a very small three-dimensional structure, it has its own value. It has a lot of surfaces. So within this very small value, I'm trying to calculate the net outward flow of that field on all surfaces. The all surfaces is included by this integration sign, and with a closed circle, meaning I have to calculate all the flows on the surfaces. So in this example, I have a small cube, right? So the cube has its value, but for the cubic, how much surfaces do I have? 6, right? So according to this definition, if I really want to calculate divergence of A within that value, I need to calculate all the outward flows or flux on all 6 sides. I calculate the flow for one surface, and then I have to add the flow, outward flow, the second surface, and so on. So totally for this cubic, I need to perform 6 calculations to accomplish this closed integration on all surfaces, right? So I'm spending a lot of time to tell you the basics, the meanings behind the mathematical equations. But this is a definition, and this definition follows directly from this sentence. The net outward flux per unit value, right? Per unit value, net outward flux. Right, clear enough? And let's move on. All right, so let's really calculate it. I have a small cubic. A cube has 6 surfaces. So I'm not going to do all the calculations. I am only going to calculate for 2 surfaces. The rest are for you to work, and I believe you learned this in the past. during your first year, freshman year. Okay, so I now have a cube centered at point P. So P has its x, y, and z values, x0, y0, z0. So as you can see, I'm using x, y, z. So which orthogonal coordinate system am I working in? X, y, z means I'm working in Cartesian coordinate. Why? Because I'm too old. You're young and smart, so I usually work in the easiest coordinate. I'm only trying to tell you, to give you a guidance to how to formulate divergence in Cartesian coordinate. The rest two coordinate systems are left for you as your homework. Okay. All right, so I have a vectorial field, A. It's also a function of x, y, z. It's not surprising because I'm working in Cartesian coordinate. So I have the x component, y component, and z component. So I have three components. Each component is having its own direction. Okay, so that's a vectorial field. So somehow, for now, for demonstration purpose, I want to calculate the outward flux on this front surface. Okay? So this is the point where we have to think. Why did the professor spend so much time in teaching you differential length, differential surface, and differential value? Let's come back to this definition. ds. What is ds? Differential surface. What is delta v? Differential value. So everything, differential surface, differential value, are actually coordinate dependent. So this is the point where in the past, you just try to memorize everything, right? Divergence for spherical coordinate, very complicated, but I'm teaching you how to derive it. If you know this definition, you understand about differential surface, differential length, differential value, you don't have to memorize anything. Okay? So I want to evaluate the flow, the outward flow or flux on this front surface. The first thing you have to ask yourself is how to properly formulate this ds, the differential surface for this front surface. You might just wonder, let me draw a picture for you. So you have a surface, right? You have a surface. Ideally, a surface has no thickness. So basically, you might be wondering, oh, the surface can actually have two directions. One is going out, the other one going in, right? So for a given surface, you can have two directions. But now the fact is, this surface is a part of a three-dimensional solid. Okay? Solid structure. This surface is the outer end of a given three-dimensional solid structure. So for divergence, we're trying to evaluate the net outward. So I'm emphasizing the wording outward, going out. So in this case, this surface has a well-defined surface direction going out. You don't want to evaluate the flow with the wrong sign for the surface. I mentioned repeatedly, surface is itself a vector. Okay? So for divergence, we're trying to evaluate the flow going out of the box. So for this surface, we want to use this direction. And for this surface, I want to use the outward. And for this one, going out everywhere, right? Everywhere going out, going out. So let's come back to the PowerPoint. So how to properly formulate this differential surface? The direction for this guy is pointing outwards, so it must be in the positive x direction. So once you know its direction is in the positive x direction, its area must be determined by the other two coordinates, right? In the y and z directions. So its magnitude, its surface area, must be delta y, delta z. Again, this is coming back to what I emphasized. For a given surface, you have a direction, and then the magnitude must be determined by the other two unit vector directions, right? So you have x direction, but then the magnitude is determined by delta y and delta z. So you know how to formulate this ds, right? So now, ds, a vector, is making a dot product to the vector field. But the vector field is having its own x component, y component, and z component. So in this case, for this particular surface, which field component of A is being evaluated? X, y, or z? Your ds is only having the component in the x direction, so only this one is being evaluated, okay, at this surface. Because you know ax dot ay or dot az are both 0, okay? So for the surface, it only samples how much flow of ax is there. Right? But then you have a question, because this cube is centered at x0, y0, z0, but you know its dimensions, delta x, delta y, and delta z. So apparently, this front surface has its coordinate value other than x0, y0, and z0. So this surface sits on the x value of x0 plus delta x divided by 2, right? It's having an offset in the x direction. So I really need to calculate, what I'm trying to calculate is ax component, but having an offset in the x direction, the x coordinate value, but not in the y and z. So how to do this? How to evaluate this? This is based on the understanding of Taylor's series. When delta x, delta y, delta z, right, it's delta x, delta y, delta z are very small, we can confidently use Taylor's expansion to the first order. So this field value is probably equal to ax evaluated at my center point plus an offset of delta x divided by 2 and multiplied by the slope, right? The physical meaning of Taylor's expansion is you're using Newton's method, right? So if you have ax itself having a partial differentiation in the x direction, you're trying to find the slope, and then you multiply by the offset, you probably know AX at this location, at the surface location. Okay? So now you have these two terms and you multiply by the surface area. So together you have these two terms. I'm using the color. So now because you have delta x multiplied by delta y and delta z, what is delta x multiplied by delta y multiplied by delta z? For Cartesian coordinate, that is the differential value that we covered. Okay, so that is differential value. We only covered one surface out of 6. So we're going to work on the second one. So which second surface are we going to evaluate? We have this one, this one, this one, the one on the bottom, and one on the back. For immediate application, we evaluate the surface on the back, the negative x direction. Okay. So now let's switch to the back surface. Again, we are trying to evaluate the outward flux. So for the back surface, its direction is also pointing out from the structure. So now the surface is pointing in the negative x direction, but its area is still determined by delta y and delta z. Right? So now this ds, differential surface, is having a negative sign. And its position is now offset in the negative direction as well. So it is situated at x0 minus delta x divided by 2. So this makes my evaluation for the flow on surface number 2 as AX. But now the x value is x0 minus delta x divided by 2, y0, z0, and multiplied by, again, ds, a surface in vector calculus, is itself a vector. So you have to know this negative sign. Right? This we know how to do already from the previous slide. We use Taylor's extension to the first order. Because you have a negative sign, so we have a negative sign. Okay. So this multiplied by this, the surface is also having a negative sign. So the differential part is now having a positive sign. But this is having a negative sign. So I'm not going to work for the other 4 surfaces, but the question is, when I evaluate the front surface, I have a positive first contribution and a positive first contribution. For the back side, the first contribution has a reversed sign, right? But not the second part. So when I add the network outward flow, only for these 2 sides, the first contribution cancels out, but the second contribution doubles. Okay? So when I add the flow on the front surface plus the back surface, I see what's remaining is the partial differentiation of the AX component with respect to X, but being evaluated at the center point of my cube and multiplied by the differential value. Right? I can repeat the process for the other 4 surfaces, but in the end, as you can see by the same analogy, whenever you do 2 surfaces, you have the partial differentiation for that given component to that given unit vector evaluated at the center and multiplied by the differential value. So together, altogether, all 6 surfaces will give you x component having partial derivative to x plus a y component partial derivative in y plus az to del z. They are all evaluated at the center point of your cube and together multiplied by the differential value. Okay, so this is our very first evaluation to the net outward flux of the field on all surfaces. So now you plug this into here, you'll be very happy because delta V is divided by delta V. Easy. Each component is having its partial derivative in that corresponding direction. Ax del x, ay del y, plus az del z. That's divergence of A. Instead of just telling you the direct result, I'm working according to the definition for you for 2 surfaces, and I'm showing you the process flow in hoping that you can easily try other coordinate systems on your own. So once you can properly formulate it on your own, you don't need to rely on your memories. Memories are really short-term. Okay? But of course, if you really need the help, our TAs are very superb. They will be willing to arrange for some special teaching hour online. I don't want you to meet the TA face-to-face. Okay? Now, generalized divergence formula. Take a look, take a good look, and think about the differential length, differential surface, and differential value that I spent so much time on Monday. Divergence of A, by definition, is trying to evaluate the total net outward flux over a small value, right? So this is the point where you really have to relate and link to what I covered on Monday, differential surface. If your unit vector is an angle, then the differential length will be an arc, right? So in that case, for this example, this H1 times H3, why is it there? When you try to evaluate the flow for your second field component, you have your surface pointing in the second unit vector direction, right? Since your field or surface is pointing in the second direction, its area, its magnitude must be determined by the differential length in the first and the third directions, right? It all makes sense. So why do I want to divide by H1, H2, H3? This takes into account the unit value, right? So try to link this to what I covered. Cartesian coordinate, differential length, dx, dy, dz. Symmetric coordinate, the differential length, dr, in the phi direction, because phi is an angle, so you need to take the arc radius into account. So it's r d phi. So this h2 is your radius. Cylindrical coordinate, the third direction is z. So the differential length is just dz. Spherical coordinate, most complicated one. In the radial direction, differential length is just dr. R is not angular, so the differential length is not an arc, it's a straight line. Theta, inclination direction, theta is an angle, so your differential length is an arc. The radius is just r, right? So the Jacobian, h2, the spherical coordinate, is just r. Phi, the same phi in cylindrical coordinate, as I mentioned repeatedly, the effective radius in spherical coordinate onto the phi direction is a projected radius. So it's r sine theta. So the arc length is r sine theta d phi. Right? So as a test and as an act of confirmation, when you go back home, you don't really need to repeat for the derivation of divergence in Cartesian coordinate, but you might want to start with cylindrical coordinate first because it's easier. It's only having this h2, having the arc. Try to derive on your own based on this definition, and you can just define your structure, your small structure, using a cube or something like that, right? So the center is R0, 0, Z0, right? Somehow, so you have only 3 surfaces. You have one surface going out, one going down, another surface having the r direction. Okay? So try to calculate the divergence and evaluate all the fields going out according to this definition. Right? And you will see whether this generalized expression holds or not. It must hold. What I'm trying to tell you is, in the future, whenever you see this ds, you should have the capability to write the generalized formulation, because when you try to evaluate the first component, you need to have a corresponding surface pointing in the first direction. Okay? A surface pointing in the first direction has its area determined by the differential length in the second and the third directions, and so on. But then you have this delta V, differential value, so you have to divide by H1, H2, H3 times the differential increments. Okay? I'm spending a lot of time on this because, to me, your ability to understand and appreciate what I'm teaching would be very important and really allows you to stand out among your classmates. So maybe in the future, if you just memorize like in the past, and if you forget during the examination or any time you forget, you don't know anything. It's just like you never learned vector analysis. But if your way to learn vector analysis, these mathematical operations, is you start from understanding the basic meaning to the physics, then there's no need for memorizing. Okay, that's my philosophy. As a student, I never was able to memorize everything, but I was able to appreciate and understand the physical meaning of this equation. Okay? Can you still hear me? All right, so I'm going to close the day with the last slide. Divergence theory. I bet all of you heard of it, but what does it mean? Divergence theory. So this is just divergence. Okay, this is just divergence, the definition of divergence. So you perform the divergence on a vectorial field. You're trying to evaluate all the outward flux on a given small value. That's the definition. So you have this limit, delta V is approaching to 0. So whenever we're trying to perform divergence on the vectorial field A, we're trying to evaluate the flows in the microscopic sense. Okay? So we're trying to evaluate, for example, I have a total of a very big structure, but from the definition of divergence of A, I'm calculating the flow of a very small box inside this structure. So for each point, for each small cube, I know its divergence value. But what about the overall structure? What if I only want to know what is the divergence of the entire structure? I want to know the macroscopic 巨观, okay? Microscopic 微观, macroscopic 巨观. What if I only care about the macroscopic view? I only care about whether this entire structure is acting like a flow source or a sink source. Well, can we move this delta V to the other side? And we change this limitation to integration, because we can just integrate everything, right? If we want to know the overall evaluation for the big structure, can we add all the results from each small cube together? Of course, yes. Of course you can do that. And that's what this integration means. For each small cube, you know its divergence value. Then we can add all the results from each small cube together to synthesize the result for the entire structure. So that's the meaning of divergence theory. It's just a way of rewriting the definition of divergence. But it's more than that. Okay, it's actually really more than that. So take a good look at this equation again. And tell me, what do you see? We still have 7 minutes. So this is the point I really want your feedback. How many students online? Only 9. So maybe in the future, we don't need to have the live streaming. Yeah, it's according to my imagination. But it's already good. I'm giving you some applause. You maintained for 3 weeks. It's already breaking my anticipation. I assumed there will be no one starting from the 2nd week. But I know this is not because of my bad teaching, but this is because the Center of Teaching and Learning Development, they're doing an excellent job in editing the video clips. So I also took a look of the live streaming recording and the edited version. I like the edited version as well. So I don't blame you guys, all right? Take a good look at divergence theory. What does it imply? Over to the right, the idea is each cube, I know its divergence, right? I know the divergence for each cube. And then somehow, to synthesize or recover the entire structure, I'm doing the integration for all the cubes. Okay? So I'm integrating over the entire volume. For each cube, I calculate its divergence, and I integrate everything. So what type of integration is it on the right-hand side? I have to integrate over the entire volume of the big structure. So this is volume integration, 体积分. The work is like at least three-dimensional, right? Three-dimensional, X, Y, Z is volume integration. But take a look at the left-hand side of the equality sign. Divergence theorem is telling you you can be lazy. If you perform the direct volume integration, it takes a lot of work. If you want to do it, fine, go ahead. But smart students can get the same result just by performing closed surface integration. Surface integration ideally is two-dimensional, right? Reduces one dimension. So this is telling you you can get the same result from both approaches, but when one student is calculating very hard divergence, performing divergence for each cube and adding all the cubes together, a smart student can get the same result maybe in 1 minute or 30 seconds because he understood what divergence theory tells you. The same result can be derived just by performing the closed surface integration of the vector itself on the outer surface of your big structure. Think about it. For you to calculate divergence of A, you need to know A initially, right? So you calculated its divergence, and you perform a three-dimensional volume integration. It takes time. But the same result can be acquired. You know A already. Once you know the structure, you know its surface. You directly perform the closed surface integration. You arrive at the same thing. So that's the real physical meaning of divergence theory. These two are equal, so you can easily and quickly derive at the same result only by performing surface integration. So you reduce your integration dimension from three-dimensional to two-dimensional. Why is that valid? Why is that valid? We need to come back to the definition. For example, I have a big structure, right? On the right-hand side, I need to calculate the divergence, the outward flow for each cube. For each cube, I have 6 surfaces. But for example, I'm taking the front example, the front side and the back side. Okay, for example. When I evaluate the outward flux for this cube, by definition, the surface directions needs to go out. Okay? But what happens when I have the second cube? When I have the adjacent second cube, which surface is the same? That surface, right? But in this case, when I evaluate the outward flux for the second guy, this surface needs to take on a direction reverse to that, right? So this is by definition. So that actually tells you when the same surface, they're canceled out because due to the direction outward, for this guy, the surface is taking the green one going into the blackboard, but for this one, although it's the same surface, but due to the definition, it has to go out. It takes on the yellow side, and these two just cancel out. So let's come back to the PowerPoint. So eventually, no matter how big your structure is, and no matter how many small cubes you have inside it, the common 共用, the common surfaces would cancel out, and leaving you only the outer surface. That's the physical meaning to this. No matter how hard you try to calculate, the inner flows all cancel out due to the adjacent commons. Okay? Leaving only the outmost surface not being canceled out. So you only have to evaluate how much of your vector field is flowing out at the outer surface. The result will be the same as you calculate the divergence of A and making volume integration. This theory will be most helpful for us to learn about electric field. So you must understand it and appreciate it. All right? So next Monday, we're coming back to curl. You hate curl the most. So do I. But next Monday, we are going to close vector calculus, and we're moving on to officially into electric field. So see you next Monday. Thank you. 这结论是我有没有麦克风没有差，我后来麦克风断。